Hello and welcome to the next section of videos in our Rust Data Structures and Algorithms course. During the coming section of videos, we are going to be looking at graphs, how to write them, how to access them, and various other challenges related to them. In this video in particular, we're going to spend some time looking at different ways to store a graph, but before we do that, it's worth spending some time looking at kind of what a graph is. In computer science terms, a graph is a set of nodes that are linked to each other by a set of edges. So here in this diagram, we have the nodes are A to H, and they are connected by various different edges. So A to C is connected by an edge, and that edge has a weight of 4. And graphs are used to solve all kinds of problems, from finding the fastest route on a map, as Google Maps would, or managing friendship, relationships, or other kinds of connections. All of these things can be modeled with a graph because every connection is represented by an edge. And for example, every person could be modeled by a node. You can store various amounts of data on each node and then use the edges to represent what joins those nodes. There are lots of different ways of storing a graph. So for this video, we're going to consider some of those options. In the following code, I have already written up standard definitions. I've brought in a ref cell because we're going to use those. I've also brought in something called a hash map. Now I've dedicated a whole section to hash maps, and that will be next section. But for now, all you really need to know is that a hash map holds a key value pair. So it will point from any key to the value that it represents, and it will do it quickly with a constant time, big O of 1. In order to do this, it requires that the elements it's using for the keys implement the hash interface. So let's start with a fairly straightforward way of implementing this. We'll just have a list of edges, and so we'll just have our V, which is a vec, and every single edge points to an ID of some form. And we may not even store the nodes, so perhaps you don't have any data to store about the nodes, so you just represent them by an ID. So for example, in the graph we started with, we're just pointing between A's, B's, and C's. There's nothing that matters on the data. So if we don't care a lot about the nodes, this is a reasonable way to store your graph. It's just a vec of edges, and you can get between the edges. It's simple. It does have some time cost, because if you want to get all of the edges from one node to another, you have to search through all of your nodes every single time. But storage-wise, it's the cheapest you're going to get. Another option is based on pointers. And in Rust, there are more challenges with pointers than there are in some other languages. As you try and write this graph as a purely pointer-based thing, you'll find that doesn't work, because how do you know which pointers are completed? It's very easy to leave yourself with unreferenced nodes that you need to delete, but you don't have a pointer to them to free that memory. So what we're going to do is we're going to store a vec of RCC, as we discussed in the previous section, and we're going to use what's called an RCC node, which we will define in a second. And those nodes will basically contain edges which link between each other. Again, it will have a data element of type T, and the edges will just be a vec of actual weak references. And the reason I've gone for weak references is because that means if we remove a node from the primary vec, then all of the weak references immediately lose their pointer to it in a safe way. So this would be good for directed graphs where between each edge there's actually an arrow instead of just a line. So because you're always pointing one way, it very makes sense to store the edges on the object they're pointing away from. Using weak pointers has the benefit, of course, that the edge will fail safely if the node has been removed from the main vec. So it's actually relatively straightforward as well to add edge data just by including that in the edge type, making that a tuple with its edge data as perhaps the first element in that tuple. So another option is to use one that is based on a hash map. It doesn't have to be a hash map, but again, as I said, hash maps have this wonderful feature that they can grab a single element in constant time. So if we define our map graph, again, this will have a T, an E, but it's also going to have an ID type. And the ID will need to implement hash because this is how we're going to reference the pointers on the hash map. Now, again, with a hash map, the value of this is when the graph gets big, and we are considering these problems. Like if your graph has only got 100 elements, it may not be worth using a hash map. It may be just as fast to just search through 100 elements. But as you get to 1,000 elements or 1,000,000 elements, absolutely you'll want to use a hash map or some form of thing that provides close to constant time for the access. So in this case, we're going to have the main map, which will be the data objects, and then the edges will be a vec of IDs. If you want to go find the edges, you're going to have to check the various edges still individually. So if you wanted to kind of speed things up, if you're planning on doing searches directly from a lot of nodes, and again, this is if each node doesn't have too many edges that it points to, you might want to add the same references to the other edges, both sides. Oh, and it needs to implement EQ, or if you want to actually find an element by a hash graph or actually search by that, it needs to check if the actual elements are the same. So we use a map pointer graph, so the ID we're going to use for both. And so again, we'll have the data, and that will be a hash map. But this time, instead of just an ID and T, well, it's going to take an ID, but for the actual data type, we're going to use a tuple, and that will be the main data, which is of type T, and a vec of ID, and that will be edge IDs. And then for the edges, we'll have a hash map, and the ID will then point, the edge will have edge data, whatever data is needed there, and 2 pointers to the hash map IDs. That should be in angle braces. Now, again, there are lots of decisions you want to make if this is which graph is appropriate for your needs. And there are other ways of kind of fudging these together to get slightly different results. For the sake of this course and for how we're going to build our algorithms, we are going to use this map P graph.